in this video I want to give some motivations on why we are studying digital control systems, so discrete time system and computer control, and more in general why we are studying control engineering. So the first part of the video will cover the topic of why we are interested in control engineering, and the second part of the video will cover the topic of why discrete time system, why digital control systems. So to explain what is control engineering, what is a control systems, I will use actually another video that is available on YouTube. And this is actually a video that won the first prize in a video contest of the IEEE Control System Society. And you can find the full link below this video. Okay, so automation or control engineering, they are more or less the same thing, but depending on which university you have attended, can be summarized as that discipline that deals with complex set of activities needed to take rational decisions in a constantly evolving and partially unknown world, relying on available and relevant information. So a control system basically is a sort of smart device that is able to make our main system behave in a certain way, a way that we have designed, even though there is some uncertainty, something that we don't know about the system, and even though the environment around is changing. One particular embodiment of control system is given by the feedback loop. The feedback loop is actually one paradigm of control system, but there are different paradigms actually. So let's look at these. And in this feedback loop, what we have is, first of all, the controlled plant. So the plant is actually the system that we want to control. So what we want is that the output of the plant behaves in a certain way. In particular, we want that the output of the plant is equal to a certain reference. So how do we design, how do we make the plant behaves in this way? So the idea of the feedback loop is the following. We take the output of the controlled plant and we measure this output, and we keep in account the fact that there may be disturbances acting on the measurements. So I measure the output and I send this measurement to the reference, let's say. So what I do now is that I compute the error between the output and the reference. This information, the error, tells me how far I am from my goal. Then I use this information to feed the controller. The controller takes the error and produces a control signal. The control signal is then fed to the controlled plant to produce, to adjust the output. So what are the control objectives that we want to realize? Well, there are a lot of different control objectives that we can realize. And the one that I just explained is the objective of tracking a reference, so that the output of the system behaves like a reference. Other objectives are, for instance, the stability. The fact that the system is stable is basically means that the system does not blow up. Another possible objective is the rejection of disturbances. The fact that there may be disturbances acting on the system, and we can design the controller in such a way that these disturbances do not affect the system. Then there is robust control that is in some way related to the problem of rejection of disturbances. In robust control, we know that there are disturbances, there are uncertainty, and we design our controller in such a way that even though there are these uncertainties and disturbances, the task is still achieved. Another objective is optimal control. In optimal control, we try to achieve our control objective in optimal way. It means that, for instance, if we are controlling a robot that goes from one part of the room to another part of the room, we may want to do it in minimum time. So this is an optimal control problem. Or using the least amount of energy. Also, this is an optimal control problem. So what I want to cover now is some success stories of control engineering. So one thing that the community studying control engineering, control theory is aware of is that the majority of the population does not know how important control systems are. They don't see that control systems are everywhere. So here I collected 3 success stories, and these stories are actually taken from a report made by the IEEE Control System Societies, where all these stories are collected. I choose these just based on my taste. The first success story is the one of Raffaello D'Andrea, that is professor of dynamic systems and control at ETH in Zurich, and is co-founder of Kiva Systems. Kiva System is this company where these robots go around the warehouse and are able to select a certain parcel and bring it to the operator. This company has been sold to Amazon in 2012 for almost $1 billion. So this is an example to show that control systems can actually generate quite a lot of money. The second example is the second success story is the one of Malcolm Smith, that is professor in control engineering at Cambridge University, and he invented the inerter that in Formula One is known as J-damper. So the inerter basically is a missing component in mechanical systems, and this component was missing until Malcolm Smith invented the inerter, and is basically the equivalent in terms of behavior, dynamics, of the capacitor. So there is an analogy between spring and inductor, damper, resistor, and before the invention of the inerter, we thought that the analogous of the capacitor was the mass. This is actually incorrect because only some specific capacitor can be are equivalent to a mass, so the capacitors are linked to the ground. But in general, capacitors are equivalent to the inerters. So the inerter is actually quite famous because it was used by McLaren secretly. I mean, Malcolm Smith sold the inerter to McLaren, and these also helped McLaren to win the championship that year. Another success story is the one of the control of aircraft. So in the 60s, there has been a very strong push in control theory to develop new techniques for controlling our aircraft and aerospace devices. And in particular, then these success stories, basically all the type of control that has been used in the control of aircrafts. For instance, in this case, the NASA Air Force Research Laboratory, Honeywell, and Lockheed Martin developed the nonlinear multivariable flight control, in which a nonlinear model of the plane is used and is currently implemented in the F-35 aircraft. I want to point out that control systems are important, not just because they can produce, a lot of money and make you win a Formula One competition, but also because when control systems fail, they can produce very important problems. The first example of failure is the example of the Gripen Fighter aircraft. And the problem is actually caused by the fact that the control systems in general, have to deal with the fact that there are also humans in the environment. And humans can actually interact with the control system and can sometimes disrupt the action of the control system. So I show you a video of this plane. The second example of catastrophic effect of failure of control systems is the Chernobyl disaster. In this case, the disaster has been also caused by the fact that the operators, the humans, were actually deactivating control systems. So this is a summarized version of what happened that night, but basically here I'm highlighting the the interaction between the operator and the control systems. In particular, what happened is that the operator first neglects to engage a power hold mode, and this caused a drop in the power. To balance this drop in the power, the operator removed several control rods from the reactor so that the power could be rebalanced. But this actually decreased a lot the additional control action that the operator could have. And with this little amount of control rods in the reactor, another system, another automatic controller, would normally shut down the reactor. To avoid this, the operator deactivated this other control system. Then what happened is that a series of chain reaction and problems created then the condition for the explosion, and since there were not enough control rods in the reactor, the operator couldn't stop the explosion. So to conclude this first part, I want to point out that control engineering requires a large quantity of mathematical tools. So control theory is about mathematics and requires then a continuous study from your part. But as I've shown you in these success stories and in these disasters, control systems and control theory is a very exciting discipline. In addition to this course, there are a lot of other courses that are offered here at Imperial College. And so here is a list of these courses, and you may be interested in attending one of these other courses, some of these other courses. So this concludes the first part of the video. And the second part of the video, I want now to explain why we are interested in digital control systems in particular. So in this slide, I'm explaining some advantages and disadvantages of control systems. So you can check the slide, but instead of reading the slide, I want to show you some specific example. So we can see here now at the board, the board is divided in two parts. The first part is a circuit, and the second part is a piece of code. So what is a continuous time control system? What is an analog control system? Well, a continuous time control system is a control system in which the control action is actually realized by means of physical components, and the variable that we're actually controlling is a physical variable. For instance, if we are controlling a mechanical system, then the control system will be made of springs and of masses, of inerters, and of dampers. If we are controlling instead a circuit, then our control system will be made of capacitor, inductors, resistance, and more complex type of components. So let's look, for instance, an example of control system, analog control system. And this is a circuit that realizes a proportional integral control system. So this is the input, so the error, and the error to the control system is the input, and the control system will produce a certain output that is actually U, and U will be the control that will be the input of the system that we want to control. And so there is a transfer function between the output U and the input E, and this transfer function obeys this law. So we see that this controller is realized by means of resistors and capacitors and no pump. What is a drawback of this control system? One drawback is that, let's say that I want to change the proportional gain of this control system. If I want to change the proportional gain, then we see that I actually have to change one of the capacitors in the circuit. So it means that I have to remove one capacitor, take another capacitor, and replace it and put it there. What if I want to replace the integral gain without changing the proportional gain? Then I have to change the resistor appearing there. So what is the problem here? The problem is that every time that I have to change the control system, I actually have to modify the circuit. And this will take time because I have actually to replace the physical component, and it requires is also expensive because every time I have to take another component. And moreover, there is another fact that if this control law, we decide that this control law is too simple, it's not enough to produce the effect that we want to produce on the system, then we will want to use more than one pole. So this control system, this transfer function has only one pole, but maybe we want to have more than one pole. And this means that basically we have to increase the amount of components. If we want to, for instance, add one pole here, we will have to double the amount of components here, and so on. It means that complex controllers will actually be very expensive. So as you can see from the slide, controllers analog controllers are difficult to implement, are expensive, and it's difficult to actually change them. So now let's look at this other part of the board. So this is a piece of code that can be implemented in a microcontroller. So here, for instance, I have two examples. So this is an Arduino, and this other one here is a Texas Instrument Tiva-C. Okay, so these are very cheap microcontrollers. These, I think, is like 15 pounds, and this is like 20, 25 pounds. And basically, this is a microcontroller that can do a lot of things, but can actually read some input and produce some output. Okay, so we can actually implement a controller in this microcontroller. So the code that we will implement will look like this. Now, this is not a specific language, it's a pseudo language, just to make you understand what's going on. So there will be a loop, okay? So this code will be executed in a loop, so continuously several times will be repeated, and will be repeated every capital T time, okay? So there is a period in which every period T, the code will be executed. And every time that the code is executed, I read the output of the system, I read the reference that I want to impose on the system, and then I compute the difference between the output and the reference, and so I compute the error. And then the controller is actually this line here. So the controller, in this case, at the time UK, okay, so at this time, is equal to the controller at the time k minus 1, so the previous controller, plus a certain number for the error at this time, plus another number for the error at the previous time. Okay? So this is actually an implementation, again, of a proportional integral controller, okay? Depending on the values of C1 and C2. Once that I compute UK, I apply the control UK using the Arduino, and then I update the values of UK minus 1, that now will be equal to UK, and EK minus 1, and now will be equal to EK, so that I can start again the loop, okay? So what is the advantage of this? Well, the advantage of this is that I can change a number here, and I just click compile, and that's the new control system. I don't have actually to do anything if not press a key on the keyboard to update my control system. I can try hundreds of control systems in 20 minutes. Okay, And another important aspect is the fact I can make this line as complicated as we want. It's still just a line of code, okay? So increasing the complexity of the controller does not create any additional expenses. There is also another advantage, the fact that this is a piece of code, and so it means that before these lines and after these lines, we can we can implement some monitoring and safety tasks. Okay, so let's look at the slides now. So this means that, for instance, I can check, okay, if the error is smaller than a certain amount, then don't do anything, okay? I can do that. Or if the error is greater than a certain amount, then instead of using this controller, use another controller. It's just a couple of lines of code that makes our control system much more efficient, much more, effective, okay, without producing any additional expenses. In this case, instead, all these actions will actually make the controller much more complicated to realize and much more expensive. Okay? What are then the drawbacks, actually, in using a digital control system instead of a control system, of an analog control system? Well, the fact that first of all, if we use a microcontroller, okay, usually we use a microcontroller to control a physical device. The physical device is a continuous time control system. This is a discrete time control system. And so we have both continuous time and discrete time components and some interfacing between these two components. And this makes the overall system more complicated. Then the analysis of closed-loop systems involving both discrete time and continuous time is often based on approximation, and we will see this through the whole course. Basically, the course is we'll spend quite a lot of time on trying to understand the effect of these approximations. Then digital controllers are very sensitive to numerical errors. So we are using a microcontroller, and so it means that if the C1, for instance, is computed in some other part of the code, let's say that there is some approximation, and then this C1 is not exactly the C1 that we want, because, for instance, this C1, for some weird reason, is realized as an integer, and so we drop the decimal part, and our analysis is that instead consider the fact that C1 was not an integer number, will not work anymore. And then there is the fact that control systems have some very not intuitive behaviors that we want, that we have to deal with. And for instance, the fact that what does it mean working in the frequency domain for digital control system? Well, in continuous time, we can understand the concept of time t and frequency domain s or jw. But in discrete time, how this frequency becomes in discrete time. In continuous time, we will have the controller and the plant that are both continuous time systems. So what happens is that the controller checks the error. Based on the error, will produce a control variable that will be fed as input to the plant. And the plant will produce an output that will be compared with the reference. In discrete time, the story is more complicated because the controller is a discrete time system, but usually, often, the system we want to control is a physical system. For instance, it may be if we are implementing a controller in Arduino, we may want to control a little robot, and the robot is a continuous time plant. So what is the problem here? The problem is that the controller will produce a control variable that is a discrete time variable. But the plant is a physical device that takes as input a continuous time input. And the output of the plant will be a continuous time output. And we have to compare this continuous time output with the discrete time reference. So to produce an error that is discrete time and can be used by the digital controller. So this means that when using digital controllers, we also have to consider the fact that in the closed loop, there are also other devices that are used to interface the continuous time world with the discrete time world. So now we briefly look at these devices and justify the fact, point out the fact that these devices actually introduce some problems in the analysis of the overall system. So the first device that we look at is the analog to digital converter. This is used to convert a continuous time signal, so the signal that is shown here, into a sequence. So let's say that we are sampling our continuous time signal periodically, then every capital T time, we take a measurement of the signal. So we produce this circle here, and then after capital T, this circle, and after capital T, this circle, and so on. And so we are reading this signal and produce a sequence. So the signal, the continuous time u of t, is translated into a sequence u of k. If we want to be precise, the sequence would be a sequence of uk capital T, because we are sampling every capital T seconds. But since we always use a periodic sampling, we just drop the capital T and we just use u of k to indicate that we are at the time, at the discrete time k. Note that we can use u of k also to indicate the case in which the sampling is done every times t highs, so not periodically every the same capital T, but at different TIs, so different, for instance, random sampling times. And in this case, the values that have been read on the signal would be u of tk. But again, with abuse of notation, we just indicate uk, because in discrete time, we just need k to indicate the evolution of time. We can forget what is the actual continuous time value of this tk or of this k times capital T. I want to point out that there are different ways to sample. So I said that we are going to use always periodic sampling time, but we may also have to use a random sampling time. So this is the case in which we have a continuous time signal and we are sampling this continuous time signal a random times ti. So I sample at t0, then after a while at t1 I take another sample, then just after at t2 another sample, then I wait a bit and I take t3 and so on. So this sampling is random. So why we want to use a random sampling time? So sometimes random sampling time have a mathematical property that we may need for our purposes, but in general, periodic sampling time is much easier to deal with. However, there are some physical constraints that that push us to use a random sampling time. And this is the case in which we have our controller, okay, that is sending the input, the control variable to the system S, but actually the control system is not physically next to the system, but it's actually sending the control variable using a network, okay? Maybe a wireless network, a Bluetooth network. But this means that actually the input is not immediately applied to the system, and the time, the delay between when the input is, the control variable is sent and when the system takes this input is actually random because it depends on the network. Another type of sampling is the multi-rate sampling, and the fact that if our system is very complicated, we may want to use a certain sampling time for a part of the system and another sampling time for another part of the system. So multiple rates, so different sampling times, are existing in the same overall system. Another type of sampling that we can consider is the multiple order sampling. And this is when, instead of sampling, for instance, every 1 second, we can sample after 1 second, 2 seconds, 4 seconds, and then again after 1 second, 2 seconds, 4 seconds, and so on. So we don't repeat ourselves every capital T, but we repeat a certain sequence of sampling times. The other part, the other devices that we have seen in the closed-loop system is the digital-to-analog converter and the hold device. First of all, I want to point out why now we need both a digital-to-analog converter and a hold device, while before we were using just a an analog-to-digital converter. Well, if we look at the digital-to-analog converter, the only function that actually does is that it takes a digital number, so a binary number, and it converts this to a physical variable. So in this case, for instance, it may be 13 volts, or it may be 13 degrees if this is an angle, or it may be 13 millimeters if this is a distance, okay? But this is just a number. Okay, so if we look at this graph, we have a series of numbers that before the conversion are binary numbers. And after the digital to analog converter, we have actually physical quantity. So for instance, here we may have 13 volts, and here we may have 10 volts, here maybe 5 volts, and so on. But what happened between these two values is not clear. So there is something missing. We still have to make this series of numbers, this sequence, continuous time. And to do so, we use the hold device. So the hold device is a device that fills the gaps. The only information that we have is discrete time information. But between the sampling times, we don't have any information. And this information has to be created. The hold device creates this information. And there are several different types of hold devices. Let's look, for instance, at this signal here. So this signal here is the original signal. We sampled the signal, and we obtained these circles here. Then we use a hold device, and we produce these different signal. So the signal produced by the hold device, this hold device, is different from the original signal. And we can imagine a lot of different ways to fill this gap. The point is that there is an infinite number of ways to fill these gaps. And this means that it's impossible to reconstruct the original system. Okay? Let's make this clear. So if, for instance, we have these three values, then one way to reconstruct is this one, using that type of hold. But another way is to use something like this, or for instance, something like that, or something like this. The point is that you can fill the gaps wherever, as you wish. Okay, there is not a rule to fill the gaps. You decide the rule. This means that it's impossible to reconstruct the original system. Okay. Oh, before going to this slide, I want to point out some particular devices. So one device is the zero-order hold that produce this behavior. So basically, you take the value, the circle, and then you keep it constant up to when you get a new value, and so on. But there are other different devices. So this type of device, the zero-order hold, is the one that we will see most of the time during the course. but we will study also the first order hold. The first order hold, instead of keeping the value constant, will preserve the slope of the value. So it will look, basically, it will produce the interpolation using the current value and the previous value. So this gives a very good approximation when the slope is constant, but when there is a change of slope, there is a quite large error. Moreover, we will see later in the course that the first order hold, so this device, will also produce more instability with respect to the device that is shown in the slide, and introduce also delays, more delays with respect to the device that is shown there. So for control systems, the first order hold is actually usually worse than the zero order hold, so than a device that keeps the value constant. That's not true in other disciplines. In other, if you are reconstructing the signal for other purposes, a first order hold may be better than a zero order hold. Here I've shown also another type of reconstruction. This is a polygonal hold. This polygonal hold works basically delaying the reconstruction of one sampling time. So basically, I wait to see what happened, okay, and then I reconstruct the signal using this information. So before reconstructing this value, I wait to arrive here, because once I arrive here, I know that the previous value is this one. So since I know that the previous value is this one, then I reconstruct, I put the value here. So I go from here to here. Then when I'm here, I reconstruct from here to here, and so I go here, and so on. The problem, so as you see, the approximation is very good, because obviously every time that you reconstruct, you build a new piece, that piece is using complete information with respect to the past. The problem of this reconstruction is that is all shifted in time, because you are waiting, so you are introducing delays. Moreover, there is also the fact that anyway, we don't know what's happening between the two sampling times. So the reconstructed signal might be this, or maybe something completely different, as it has been shown here. In addition to these problems of sampling and reconstruction, because we are just shown basically here that sampling and reconstructing the same signal is impossible, and so we will have approximations and we will have errors. There are also other distortions that are introduced when using digital to analog converter and analog to digital converters. One of these distortions is the problem of quantization. When we go from analog to digital, what happens is that we have an analog value that, for instance, it may be 2.312 volts, okay? The point, this is an analog value. It means that it's a value that, in general, can have an infinite number of digits. When we go to the analog to digital world, so we go to the digital digit, we cannot have an infinite number of digits, because the number of digits is given by the architecture of your microcontroller. So this means that we have to approximate this number, okay? For instance, here we may have that the original value, the original function, the continuous time function is this one, okay? But when we are going to sample, we are going to convert this from analog to digital, we cannot represent this value, okay? Because the least significant bit can represent this value or this value. And so we have to pick, and we pick this one. Here we are lucky, and we pick the right one. Also here we are lucky, but here we see that there is some error. And here again there is error, okay? This is due to the fact that the least significant bit is not small enough to represent this value with this type of precision, okay? Okay, so with this, I conclude this first video of motivation of why we're studying digital control systems. So in particular, why we're studying control systems and why instead of looking at analog systems, it's important to study digital system for all a series of advantages. At the same time, digital control systems introduce several problems, approximations, and error that makes the analysis and the control more complicated.